Quick question. If handed you a single 3 megabyte photo and sent you back to the 1980s, you might need multiple disks just to carry it. Now here's the plot twist. Today we don't just store data on plastic or metal, we're learning to store it in molecules. Storage evolves for 3 reasons. Every single time. More capacity, faster access, smaller space. And each leap changes what humans can actually do with computers. Floppy disks were the original portable file. You didn't upload your project, you carried it. Which floppy became the last mass-produced standard, and the 3.5-inch floppy became the last mass-produced floppy format, replacing 5.25-inch floppies by the mid-1990s. What was the real problem with floppy disks? But floppies had a problem. You weren't just storing files, you were storing your anxiety. Bend it? Bad. Dust? Bad. Magnets? Game over. And now you know why the save icon is a floppy, even if you've never seen one. Then came the giant leap. Magnetic disk storage, hard drives. In 1956, IBM shipped the first commercial hard disk drive, Model 350, as part of the IBM 305 RAMAX system. What was the biggest breakthrough of the IBM 305 RAMAX system? A. It stored data on tape faster than disks. B. It enabled real-time random access to data. C. It was the first CD-ROM storage system. D. It used flash memory instead of spinning platters. You guessed it right. Answer is B. Real-time random access. The RAMAC disk used 50 platters and stored about 5 million characters, enabling real-time random access compared to tape or punched cards. Translation: storage stopped being play the tape until you find the part, and became jump straight to the data now. Next era, optical storage, CD-ROMs. Now, software, games, and data could be duplicated and shipped cheaply. A standard CD-ROM commonly holds around 650 megabyte, and later 700 megabyte variants became common. This was the install from disk generation. The computer at home suddenly had access to bigger software and bigger media. If you've ever heard insert disk 2, you lived this era. Then came flash memory, the technology that made modern portable storage truly practical. IEEE Spectrum highlights Toshiba's NAND flash memory as a key milestone and ties it to the work of Fujio Masuoka. The big upgrade was simple: no moving parts. That means better shock resistance and more portability compared to spinning media. This is the foundation under USB drives, memory cards, and eventually, SSDs. SSDs changed the feel of computing. SSD stands for solid-state drive. Boot times collapsed. Apps opened faster. Systems became more responsive because storage latency dropped. And here's a key technical shift. Interfaces and protocols had to catch up. SATA 6 GB per second is roughly what max speed. A. 60 megabyte per second. B. 600 megabyte per second. C. 6,000 megabyte per second. SATA 6 GB per second is often described with a theoretical max throughput around 600 megabyte per second. But SSDs pushed for something designed for flash performance, so NVMe, non-volatile memory express, became the modern standard for PCIe SSDs, built for lower latency and scalability than legacy interfaces like SATA. Human translation: SATA was great for an HDD world. NVMe is built for an SSD world. Storage didn't just get bigger, it got fast enough to stop being the bottleneck. Now, the science fiction chapter that's actually real research: DNA data storage. The physical molecule you write data into by arranging its 4 letters in a sequence that represents your digital bits, is zeros and ones. DNA storage encodes digital bits using which 4 letters? Instead of storing bits as magnetic polarity or electrical charge, you encode data using DNA's letters, A, C, G, T. Those letters are DNA's 4 chemical bases, adenine, cytosine, guanine, and thymine, like a 4-letter alphabet you can write data with. Microsoft Research openly describes DNA storage as an ultra-dense archival direction and has published work and prototypes in this area. Step 1. Encode binary data, sequences of ACGT. Step 2. Write you synthesize DNA strands. This is currently costly, slow. Step 3. Store DNA can be stored compactly in controlled conditions. Step 4. Read you sequence the DNA and decode back to digital. In DNA data storage, what's the correct end-to-end pipeline described in a peer-reviewed paper? A University of Washington paper details it clearly: encode, synthesize, store, sequence, decode, along with engineering challenges and error correction needs. And the why is insane. Research literature discusses DNA's theoretical density at extreme scales, useful for long-term archival concepts, not your daily laptop drive. So no, DNA storage is not here to replace your SSD for gaming. It's targeting cold data, archives that must survive and stay compact. It's like compressing a warehouse into a vitamin capsule, but for data. DNA storage is still early. Writing, reading speed, and cost are major barriers today. Best storage for data you'll access rarely, but must keep for decades? A. RAM B. HDD C. SSD D. DNA storage. Archival concept. You have guessed it right. Answer is D. DNA storage research is positioned for archival, ultra-dense, long-term storage concepts, not everyday speed. We went from fragile floppies to spinning disks, to laser disks, to instant SSDs, and now we're learning to store information inside molecules. Storage didn't just evolve, it expanded what humanity can remember. Subscribe for more tech time travel and jump into the tech playlist right now. One video, one brain upgrade. Comment floppy if you used one. Comment DNA if this blew your mind.